The atomic mass of an element can be found by looking at the periodic table. But did you know that you can actually calculate the atomic mass of any element as long as you know the natural abundance of its isotopes? That's what we're going to be working on today. So if we look at the periodic table, we can see that each of these atoms has its designated atomic mass. So that's this value here. At the bottom, it's the number with the decimal points. And this is the average mass of an element that when we take into account the natural abundance of each of the isotopes of that element. And we're going to learn how to calculate that. So first we're going to use chlorine as an example. So chlorine on the periodic table is right here. It's element number 17. And as you can see, the atomic mass is 35.45 AMU, or atomic mass units. So let's write that down. So we have chlorine, chlorine has an atomic mass of 35.45 atomic mass units, and we're going to learn how to calculate that. So some information that you need to know is that 75.77% of all chlorine atoms are Cl35, which has a mass of 34.97 AMU. So as a little bit of a review, do you remember what this notation means? So remember that this is the chemical symbol plus the mass number. So the Cl is the symbol, the 35 is the mass number, which, if you recall, is the total number of protons plus neutrons. So 75.77% of all chlorine atoms have a total of 35 protons and neutrons, and they have a mass of 34.97 AMU. That's what all that information means. The remaining 24.23% is chlorine 37. And this has a mass of 36.97 AMU. And we can use those numbers to calculate this value here, the 35.45. And that is our total atomic mass units, so our total AMU. So we know that our total atomic mass is going to be equal to the sum of the natural abundances of both of these isotopes. So the way that we calculate that is 34.97, so we take the mass of the first isotope and multiply that by the percentage of the abundance of that isotope. So that is going to be 0.7577. Remember that if we are changing a percentage into a decimal, all we do is we move this decimal point 2 spaces to the left to get 0.7577. In my class, you can write 0.7577 or you can write 0.7577. I don't care whether or not you include that 0, it's the same number either way. And then we add the next isotope. So then we have 36.97, that's the mass of the second isotope, times the natural abundance of that isotope, which is 0.2423. So go ahead, plug that into your calculator, see what you get. You should get that the total atomic mass is equal to the atomic mass on the periodic table, which is 35.45 AMU. So that's how you solve one of those problems. Now let's do another one as practice. So let's use copper as an example. So copper is Cu, and it has two naturally occurring isotopes. 69.17% of the isotopes are Cu63, and Cu63 has an atomic mass of 62.9291 AMU, atomic mass units. So the remainder is Cu65 with an atomic mass of 64.9278 AMU. So sometimes these problems aren't going to tell you the percentages of all of the different isotopes. So if it only gave you this information, what would you have to do in order to figure out the percentage of the second isotope? Think about that for a second. So if you're only given the percentage of one isotope, but you know there are two of them, because they're percentages, all you would have to do is subtract from 100. So you would do 100 minus 69.17, and you would get that the remainder is 30.83, and that is going to be the percentage of isotopes, the percentage of copper that is the copper 65 isotope. So now we do just what we did above to calculate the atomic mass. So we have the atomic mass is going to be equal to the mass of the first isotope times its percentage, written as a decimal, so 0.6917 plus 64.9278 times 0.3083. So let's pay very close attention to our significant figures when we're solving this problem. So this value here, the mass, this is a measured value. So we have 6 significant figures here. All of those digits are significant. And then in the second value, the percentage, we have 4 significant figures. So when we multiply those two numbers together, I know you would probably be doing this entire thing in your calculator, but I actually recommend going step by step because it's easier to follow through with your sig figs. But so when you do this step by step, for the first step you would get 43.5284 plus 20.0172. So because this number here has 6 significant figures, but this value only has 4, then this first number is going to have to be rounded to 4 significant figures. So that's 1, 2, 3, 4. So that 2 is going to be our last significant digit. And then on the other side, we have, again, 6 sig figs and 4 sig figs. So this one, so we have 1, 2, 3, 4. That one is going to be our last sig fig there. So when we add those two values together, we're going to have 43.5284 plus 20.0172. So in this particular problem, both of these values have the last significant digit in the hundredths place. So that makes this problem pretty easy to solve. So we just solve this problem mathematically to get 63.5456. And then we have to round to the correct sig figs. So since both of these have the last significant digit in the hundredths place, we're going to round to the hundredths place. Because the value to the right of that 4 is a 5, it gets rounded up. So our final answer to the atomic mass is going to be 63.55 AMU. So that's how you solve the atomic mass of an element.